second order is actually a D minus BC. That was the beginning. That was where we started on Wednesday, and then gradually we built up a method for finding a third order determinant. I am not going to do a revision on that right at this moment because all today's lecture is devoted to, well, basically all determinants. And so, I am now going to erase this unnecessary stuff. Now let's remember what we did. We had the minor. We had an idea of a minor of a determinant. What that meant was we simply deleted that row and that column from the matrix, from the determinant, and we got a determinant that is smaller, one order less, one order lower. That was n minus 1 rows now and n minus 1 column now. So for example, if you have a determinant, in this case I put stars instead of all the elements so that we don't have to worry about those. So what we do is, suppose this element is in the row number I and column number j. So what we do to obtain the minor ij was we simply, okay, it looks like it's in the wrong place. Everything is in the wrong place. All right, I will cancel this and I'll do it by hand. So this element is row number I, in this case it looks like 2, and column number j, that is, looks like 3. So what we do is we cross out that row, that column. So if in the beginning we had the determinant size 4 by 4, now we have a determinant size 3 by 3. This is the minor. So this is actually the minor with number ij. So row I, column j. We have a big determinant, 4 by 4 or sometimes larger, but when we find a minor, that minor actually is one order less. One row less, one column less. And so we already saw last time that for the third order determinant, that was A11, A12, A13, A21, A22, A33. Now I am consciously using the standard notation for all elements. Last time I said ABC. Now, okay, this was 2, 3, and this is 3, 3. And this determinant then could be expanded by the first row. So we said, all right, it could be A11 times its minor minus A12 times its minor plus A13 times its minor. But then we said, yes, we could do it by any other column. That is, we take all elements of a column or of a row, multiply each element, as you see, by the corresponding minor, and then add them up using a certain principle for signs. And the principle was this. If we expand through the first row, we use signs plus, minus, plus for these products. If we expand through the second row, we use minus, plus, minus. If we expand through the third row, we use again plus, minus, plus. And through the columns now we see this diagram actually tells us exactly the same thing about the columns, how to deal with the columns, how to manage these things with columns. And the trick was that we could expand this determinant through whichever row we like or through whichever column we like. The rule is we take the elements from that row or column, multiply each element by its minor, and then use this sign diagram to add all these products up. So that was what we did last time. Now today, okay, I'll get rid of these. Today, now the next thing is cofactor. What is a cofactor? Minor, that was simple. We just crossed out one row, one column, and we got a minor. from the remaining things. Now, the cofactor is almost the same as minor. The cofactor is almost the same as minor, and it is defined as you see. The cofactor with number ij, this again, row I, column j, is defined as -1 to power I plus j times the minor, corresponding minor. Now we have to think about what is -1 to the power I plus j. What is that? We know that -1 to taken to an even power is +1, and to an odd power is -1. In other words, this is either 1 or -1, depending on the sum, odd number or even number. So what happens is that cofactor is the same as minor. If -1 to the power I plus j is 1, then we see that it's this is okay. Mr. Crystal, please could you put your full name there? I'm looking at chat at the moment. I cannot put you on my student list if you only have an incomplete name. And so, if I plus j is even, then we have cofactor is the same as minor. If I plus j is odd, then cofactor is the opposite of the minor. But if we think about it, these signs are actually the same as we had in this chessboard principle diagram. Remember, for the 3 by 3, we had this. For 4 by 4, we have just one extra row, one extra column, but this chessboard principle, alternating sign principle, remains. So this is the same thing, because at these positions, see 1, 1, 1 plus 1 is 2, 1, 3, 1 plus 3 is 4. So all these plus signs are in fact in the positions where I plus j is an even number. That is 2, 4, 6, and so on. And all those minuses are where I plus j is an odd number. So in fact, this plus minus diagram is in fact very useful, so that you do not have to use that previous thing. You don't have to do this. You don't have to do this. All you have to remember is the plus minus diagram, this chessboard principle diagram, and you will know whether you have to keep minor as it is or put the sign that is opposite. Why cofactors? Why do we do these cofactors, in fact, actually? That is because now, if we want, for example, to expand our good old, let's go back, this third order determinant by one row. In this case, it is expanded through the first row, right? So, in fact, instead of thinking plus minus, I can write A11, C11 because it's the same, plus A12, C12, because now this minus sign is included in the cofactor. Minus M12 actually is cofactor 12. And M13 is the same as cofactor 13. In other words, I can have a formula for the determinant without thinking about plus minus. In the end, when you do it practically, it makes no difference because you still think about where do I put plus and where do I put minus. When you find the determinant in practice using the numbers, so who cares whether we think plus minus plus for this or plus minus plus for putting it into the cofactor as an extra factor plus 1 or minus 1. There, it makes no difference. So this is perfectly fine using the minors when you are computing a certain determinant for practical purposes. However, for theoretical purposes, if, for example, in advance, I don't exactly know whether my row number is even or odd, or column number is even or odd, so that I can write a very general formula without having to think, okay, I have to write plus minus plus if I is the row number is an odd number, and minus plus minus if the row number is an even number, for example. I don't have to think about that. And so I can write, okay, this was this, yes, the cofactor thing. And moving on to the general definition of a determinant now. Remember that minor is also a determinant. Cofactor is a minor with maybe an extra minus sign in front. Maybe, sometimes, not all of them. So basically, what we did in this previous case with the third order determinant, we wrote third order determinant using second order determinants. Similarly, we will define a fourth order determinant, 4 by 4, using third order determinants, which are minors for this. And so, suppose we have an nth order determinant, 2 by 2, 3 by 3, 4 by 4, and so on. And we need to find its value. So suppose we already know how to find the 2 by 2, 3 by 3 determinants, but what if the determinant is bigger? What if its size is greater? So if we take row number R, I chose R because that makes sense for the word row. So if we choose the row number R, then the determinant can be written. We see AR1, CR1, AR2, CR2. In other words, we are going through the row R. The first index is R everywhere. So we are still moving through the same row, number R. We are multiplying each of the elements by its own cofactor, that is minor, using the sign, the extra sign minus sometimes, when necessary. Second element in the same row multiplied by its cofactor. Third element in the same row multiplied by its cofactor, and so on until we reach the end of the row. So using cofactors instead of minors actually saves us from saying, okay, we use plus minus plus in this case and minus plus minus in that case. We can simply write a single formula. Just remember that the cofactor extra signs follow the chessboard rule. And if we are expanding by the column number C, we do the same thing. Now pay attention. For each of these products, the second index is C. Second index is C, which means we are moving through the column number C in this case. So the column number C, we are moving through it. And again, of course, judging by the diagram, by the chessboard principle, this plus minus sign diagram, some of these will have an extra minus in front. Alternating signs, plus minus or minus plus minus. That's depending on the number of the row or number of the column. Now let me see what is next. Properties. Instead of properties, perhaps I will simply give you one example. Let's take a fourth order determinant. Let's take the fourth order determinant. Let's say 1, 2, 3, 4. We will not compute it at the moment, just write it. 0, minus 1, 2, 7, minus 3, 4, minus 1, minus 2, 5, 0, 3, minus 1, something like that. So if we want to expand, if we want to find this fourth order determinant 4 by 4, we can use, let's say, if we use the first row, remembering the chessboard principle, these will also help us with the signs of the minors. Sorry, that was not the thing I had to do. All right, go back. Plus, minus, plus, minus, minus, plus, minus, plus. If I'm going through the first row, I have to start by first element as it is times its times its cofactor, and let me see. So I am eliminating that row, that column, and its cofactor is, you see, the remaining minor, which is a third order determinant. So it will be minus, it will be minus 1, 2, 7, 4, minus 1, minus 2, 0, 3, minus 1. So it's plus. Now the next element would be with a minus, as we can see here. So it will be minus 2 times its cofactor. Again, we cross out that row, that column, and we see the 3 by 3 determinant that is remaining. So we have 2, 0, 2, 7, minus 3, minus 1, minus 2, 5, 3, minus 1. Next one would be again with a plus sign according to this. So it will be 3 times its corresponding minor. And finally with a minus will be minus 4 again with its corresponding minor. Similarly, we could expand through the second row, for example, or through any column. Again, if I expand through the second row, I would have to use the signs from the diagram of the second row. Now, what I wrote were minors, but just remember that if I take this minus and multiply by the value of that minor, I get the cofactor. So this minus is included to create the cofactor. Here we do not have a minus, we have a plus, so that plus goes into the cofactor. So the minor is the same as cofactor in this case. It's simply as an example. We will work through this. We will have more examples. It was just, let's say, the first attempt. And then remember that the third order determinant, each of these could be now written using the same principle. So in fact, the determinant, the first minor, this determinant would actually be written again as consisting of 3 terms, 3 factors, 3 products. And each of these 3 products would contain a 2 by 2 determinant, a minor for this one determinant. So you see that if we follow through everything, according to the definition, we might actually have a lot of work because here.
I'm not hearing your voice, miss.
Anyone else?
I don't
Then
know, ma'am. I don't have this problem.
so okay. So it might be a problem with their speakers, perhaps not the microphone.
Ma'am, in the second step, after opening this determinant, we have to same
Yes,
follow
yes.
the plus minus plus
We would
system.
need, yes, we would need in the next step, we would need to open up this and this and this and this. See how much work it is. So evidently, we need to have some properties of determinant. We need to find a way to make it faster, shorter, because this is really a lot of work.
But now, if we don't know the properties, we have to open this determinant simply. We have to follow the plus minus plus system.
We have this plus minus plus system here, but in order to open this, we use this system. But we cannot do anything without opening. Without opening this, it's nothing. So we can skip opening this up and up and up again if we know the properties of determinants, if we know some shortcuts. And now the properties of determinants are all about how to find shortcuts, how to do it faster, because by definition, we have to do it exactly like this, which is, of course, not very pleasant. And so I am going to erase this now because that was just an example. So properties of determinants. So the first property, if I interchange any 2 rows or columns, the sign of the determinant simply changes to the opposite, but the absolute value remains the same. How is that? I can show you with a 2 by 2 determinant. A, B, C, D, we know that this is AD minus BC, according to one of the very first definitions of determinants. Now, if I exchange the rows, I have C, D, A, B. Having exchanged the rows, I see now we have BC minus AD, so it's indeed the opposite. So if this happens in a small determinant, like 2 by 2 determinant, then, for example, if I have a bigger determinant, a 3 by 3, if I expand it by the row not exchanged, I will see that all the minors will have changed the sign to opposite, and therefore the whole determinant changes the sign to opposite. So this is an illustration, but in principle, we see that if the determinant, for example, 1, 5, 3, let's say 7, is 7 minus 15 is minus 8, then I might exchange 2 rows or 2 columns. Now let's try the columns, 5, 7, 1, 3. Now I have 15 minus 7 is plus 8. And this happens also in bigger determinants, in higher order determinants, 3 by 3, 4 by 4, and so on and so on. What this says, what this property means is, if we want, if it serves our purposes, whatever those purposes are, we may exchange 2 rows, interchange 2 rows of a determinant or 2 columns, but at that we need to put an extra minus sign in front. We simply understand that we have to put an extra minus in front. So, in fact, it would be A, B, C, D. And if I exchange the 2 rows C, D, A, B, these determinants are simply opposite numbers. So I can exchange the 2 rows, but that means I need to change the sign in front of it. Sometimes we will need to do this. Sometimes this will actually be helpful. So this operation is in fact important, not only for matrices and determinants. It will be important further on in the next unit when we discuss vectors and vector coordinates. Yes, we will use determinants for those as well. Now I am erasing this and getting the next property. So, for example, okay, this is simply an example. Again, in 3 by 3, if I, for example, exchange, okay, this had to be 2. Sorry, this had to be 2, my mistake. If I exchange the second row and the third row, what happens is the determinant simply changes its sign to opposite. Simply changing its sign to opposite. So this sometimes is necessary. Sometimes we need to get a certain number in a certain place. And for that purpose, sometimes we will want to exchange 2 rows, for example. If I want this number to be 1, but I see that A3 is 1 and A2 is not 1, if I want 1 in the top left position for some reason, and sometimes we really need it, in that case, I would exchange the first row and the second row completely, all elements, but at that I would put an extra minus in front so that the determinant does not change, the expression does not change the value at all. And this is the same example with the small determinants, with the 2 by 2 determinants. So this is something we will do. This is something we will do. It will be useful. Next property. If we multiply a row or a column of a determinant by a constant, whole determinant by that constant. So this means we can simply take a common factor out in front of the determinant. Because if I take this determinant, multiply one of the rows by some number k, as a result, I see that the determinant has been multiplied altogether by this number. So that means I can actually take a common factor from a row or a common factor from a column in front of the determinant. That can be useful. Again, we can demonstrate this. We can demonstrate this using the 2 by 2 determinants. So see, I have multiplied the second column by number k, then I write the determinant according to the definition of 2 by 2 determinant. I see that I could take k outside, so yes indeed, the whole basic determinant ABCD has been multiplied by the number k. You see that we are not multiplying the whole determinant, only one row, one column is multiplied by this. And it's enough, the whole determinant is multiplied by that number. So basically, again, we can prove it inductively. We can demonstrate it very clearly that it happens with 2 by 2 determinant. So to prove this for a bigger determinant, we should simply expand it, for example, through the third row, through the row that is not multiplied by it. And we will see how this k number actually shows up. Or we can expand it through the row that is multiplied. It will be the common factor, as you know, from the expansion. You can take it outside. You can take it you can take it in front of the whole expression as a common factor. So interesting things that change the properties of determinants. Now, is there anything that would not change the property of a determinant, the value of the determinant? And it turns out that, yes, indeed, the determinant remains the same, doesn't change the value at all. If we take one row, multiply it by some number and add it to another row, like this. So for example, I have the determinant ABC from 1 to 3, and I decide that I take the first row. So what happens here? What happened here? I took the first row, multiplied it by number k, and added to the third row. So basically now this third row plus k times row 1 from the first matrix. And we simply substitute third row by third row plus something else, plus another row. Please note that all the elements of the first row were multiplied and added down. It's not the same number being added, but a whole row plus row. We are adding rows together. We are multiplying rows of the determinant by some number. So in principle, yes, we will usually do it this way, in this direction. I gave you this example because I simply wanted, if I have added the first row times k to the third row, then I have the same determinant as the original determinant, same value. But in practice, we will go this way. We will start by some determinant and we will decide, okay, I want to multiply the first row times 2 and add it to the third row. Why is that? We will see. There are very good reasons. Sometimes we, as I already said, we want certain numbers in certain places, usually zeros or ones. Actually, as you saw from that expansion, if we have zeros in some row, it would be very good because then we could expand through that row and save some work for ourselves. So, and again, I will erase this. And again, you see that we can, in fact, let's say in this case, I gave you an example with the first column multiplied by k and added to the second column, as you can see here, expanding the determinant, opening up, and we see how AKC actually disappears, cancels out, and we get the original determinant as it was before. So similarly, we can actually prove this property for any determinant, for any order determinant. We will see how to do this in practice very, very soon, and why we would like to do it as well. Now, let's see what's next. Zero determinant. Sometimes it's actually very useful to see, oh, this determinant will be equal to 0, and save ourselves work. We don't have to expand. If I see clearly this determinant must be equal to 0, I don't have to open any parentheses. I don't have to expand this determinant. So first of all, the determinant or a determinant equals 0 if, for example, one row or one column consists only of zeros. You can imagine that, for example, if I have 0, 0, 0, 1, 2, 3, 7, minus 8, 5, something like this. I just expanded through the first row. I have 0 times minor, minus 0 times minor, plus 0 times minor. Of course, it's 0. Because if I expand it through this 0 row, then the result can only be 0. All elements, all terms, all products will be zeros. That would be one possibility. Next, two rows or columns are identical. If two rows or two columns are identical, then let's say 1, 2, 3, 1, 2, 3, and 4, 7, 0, for instance. Remember, we could subtract or add. We could add any row to any other row multiplied by a number we like. So if I, for example, if I decide that now my row 2 I can multiply row 1, first row, by minus 1, that is, I can subtract first row from the second row, the value of the determinant will be the same. So I will have 1, 2, 3, subtracting 1 minus 1, 2 minus 2, 3 minus 3, 4, 7, 0. And I see that if I expand this determinant through second row, it will of course be 0. So because I may subtract or add any row to any other row or any column to any other column, actually I can create many zeros. And that's one reason why I actually like to do that, create many zeros, to simplify finding the determinant. Sometimes to make sure that I can see this will be 0 and I don't have to work too much to find it out. Sometimes we will see another case. I think that's the next one. Yes. One row is a constant multiple of another row or column. For example, column 2 equals minus 2, column 3. So column 1 is minus 2, column 3. For example, all right, I have 3 by 3 matrix. Let's say 1, 2, 3, minus 2, minus 4, minus 6, according to this. I'm giving you an example. And here we might have 1, 5, 7, for instance. Doesn't matter what. So in this case, I could say that column 1 plus 2, column 3. Remember, I may do this. I may take one column, multiply it by any constant, and add it to another column, and nothing changes in the value. So as a result, now I have 1 times 2 plus minus 2 multiplied by 2 and add is 0. 2 times 2 plus minus 4 multiply and add is 0. And 3 times 2, 6, added to minus 6 is 0. And I don't have to change anything else in that determinant. As you notice, I don't change the column that I multiplied. I only multiplied for the purpose of adding it to the first column. I leave it not multiplied by minus 2 where it is in its old place. It stays. It's like it reaches out long hands, long arms to destroy the first column. But by itself, it's sitting there safely. So we see again, if I have this property, I can actually use this column 3, in fact, to make all zeros in column 1. And so the determinant actually is equal to 0. And finally, linear combination. This is a new idea. What is a linear combination? Linear combination of two mathematical objects is exactly this. Multiply each of these objects by a number and add them up. So row 3 is 4 row 1 minus 3 row 2. So that means row 3 is a linear combination of those two rows. That is a linear combination of those two rows. And that means that I can actually, eventually, I can work with these two rows, multiplying them correctly by good numbers and adding them down to the third row, just to make zeros there. And then we have more properties that are, let's say, more, they are useful. So if I have to multiply two matrices, determinant of the matrix product A times B, then the determinant of this matrix product is actually the determinant, the product of the two determinants. For that, yes, some people have missed it. You have to catch up. We need to multiply the matrices A and B. If we multiply those two matrices, then the determinant of the new matrix will be the product of the two corresponding determinants. We can try it out. Let's take something simple and small. Let's take matrices 2 by 2. 2, 3, 1, minus 4. Let's multiply it by 1, minus 1, 5, 0, for instance. We know that if this is the matrix A, then the determinant of the matrix A, 2, 3, 1, minus 4 straight lines, minus 8, minus 3 is minus 11. And the determinant of B, if this is the matrix B, the second one, would be 0 minus negative 5, and that is 5. Now, the product of these two matrices, AB, the product of these two matrices, now let's remember, we went horizontally through the first matrix and vertically through the second matrix. Step by step, multiplying two numbers at a time. So 2 times 1, 2 times 1, then we hop on 3 times 5. So 2 times 1 plus 3 times 5. Second row, first column, we are going through second row, first column, 1 times 1 minus 4 times 5. The elements of the second row of first matrix times elements of first row of second matrix. And now, first row, second column will be 2 times minus 1 plus 3 times 0. And second row, second column, we take second row, second column, 1 times 1 minus 4 times 0. So the product, matrix product is 2 plus 15 is 17. 1 minus 20 is minus 19. Minus 2 plus 3 is simply minus 2, and 1 minus 0 is 1. And now let's see, the determinant of this, AB, is 17 minus 2 minus 19, 1. We see that this is 17 minus 30, 38. I think I missed some signs somewhere. 38, because there had to be a different sign. Let me see. 50, 70.
First column, second row.
Which one? Which number is wrong? Just tell me which number is wrong in the matrix, this one.
It will be minus 21.
It will be minus 21.
Not.
Wait. In which, here, let's see, 1 times 1 is 1, minus 4 times 5. It's minus 19 here, I think. Because this is plus times plus, it's 1 times 1, minus 4 times 5 is minus 20. So it's minus 19. Minus 38. It should be something, somewhere. I made a mistake with signs, I guess. My guess is I made a mistake with signs. 17 and 1. Could be something. Let me see. Oh, it's this one. This is minus No, second column. Yes, second column. This is minus 1. This is minus 1. Yes, minus 1. That's. So this is minus 1. So it's minus 17. Minus 38 is minus 55. Thank you. This is minus 55. And we see that the product of the two separate determinants is minus 55 as well. Minus 55 is the product of the determinants, and at the same time, the determinant of the product is also minus 55. If we get the numbers correct. So we see actually we see a serious problem when we are doing this. We have to be very, very careful with the numbers. Very, very careful, because it's so easy to lose a sign. It's so easy to get a minus lost, or a minus where it's not supposed to be. So we simply have to be careful. Simply have to be careful. It's the matter of carefulness. All right. And another one, so of course they must be square matrices and of the same order, otherwise they cannot be multiplied if they don't have the same order, and they do not have determinants if they are not square. So square, because the determinants must exist, and same order so that we can actually multiply them. And here, determinant of some matrix times k is k to the power n times the determinant, because k times matrix actually means we multiply all the rows by the number k. And so from each row, we bring out the common factor k, and if there are n rows, then we have k to the nth power in front. So this is interesting. You multiply a matrix by a number. No, the determinant is not multiplied by the number, but it's multiplied by the number to the power n. Now let's have a look at some examples. Let's have a look at some examples. I had to make a light background because this is actually a picture from somewhere, and I couldn't make the matrices white. I am trying out this dark screen because after 3 lectures, my eyes simply cannot hold the white background anymore. So why is each of these determinants equal to 0? In fact, we could say, for example, for this one, why is this determinant 0? It's because the second column is actually 3 times the first column. And remember, we had this rule: if one row or column is a multiple of another row or column, then the determinant must be equal to 0. Of course, in this case, you could open it and actually see it for yourself that it is 0, but the idea is that you should notice that the second column is 3 times the first column, which by itself means determinant is equal to 0. For a larger determinant, you don't want to waste too much time finding the value of the determinant only to discover that it actually is equal to 0. So in B, we see very clearly it is the second row consisting of zeros only. So one row is only zeros. That means determinant is 0. That's enough. So as soon as you see something like this, you can know immediately determinant equals 0. In C, again, I would say it's comparatively easy to notice. First row and third row. So row 1 equals row 3. This means the determinant equals 0. This determinant is 0. We don't have to do anything else because these are, let's say, the rules or the conditions for 0 determinant. In D, can you notice the problem in D? Why would this determinant be equal to 0?
May I say?
Yes, of course.
First column and third column are constant multiple
You
of
could
each
say
other.
proportional. For example, you can say they are proportional. So actually, column 3 is minus 2 times column 1, for example. So one column is a multiple of another column, or you could say the columns are proportional. You can think of a proportion to minus 4, 0, 0, 3 to minus 6. The three ratios are the same. That also could be used. E, this is a little bit tricky, but not so much. You can see in E that row 3 is actually row 1 plus row 2. If you add the first row and the second row, you get the third row, which means if you subtract first row from third row and second row from third row, you will actually get the row consisting of all zeros, if you want to prove. But as such, this is enough. This is the linear combination. Third row is linear combination of first and second row. Now two fourth order determinants, bigger ones. Again, something could be noticed, something could be seen. Something could be seen, and what is that? So rows don't seem very similar, but if we see the second column and the fourth column, you see again we could say that column number 4 for this is actually minus 1.5 or minus 3/2 times column 2. So it's just finding the correct number, finding the correct factor. So it takes experience. One thing you don't have to worry about, I will not give you a matrix in a test, for example, unit test, for example, or examination, and say, okay, now you have to notice that this determinant is equal to 0. No, it's simply to practice the idea, understand the idea, because sometimes what is necessary, when these things are obvious, it's actually a very good thing to notice them when they are obvious. In this case, it's not obvious simply because the determinant is too large. 4 by 4, usually you don't have the time to waste to examine all the numbers. What if I can discover something? And what if you cannot? What if the determinant is not equal to 0? So, of course, it's useful if it's very obvious. For example, I would say in number 1, 2, 3, it is very obvious, and this would be very useful to understand. Now in G, I guess I will have to tell you, because otherwise it might be somewhat difficult. Row 3 in this final determinant, in this seventh, G, it's 7, in the seventh, we actually have let's put it this way, 2 row 1 plus 3 row 2 is actually equal to row 3. We might understand that, for example, if we look at the 0 elements in the upper 2 rows, and we could say evidently it looks like the second row is multiplied by 3 and the first row is multiplied by 2. Of course, we need to check. Of course, we would need to check that the other numbers also fit. So 2 minus 3 is minus 1, and 4 plus 15 is 19. So these also work. But as I said, it's not something I require you to do just at any given moment. It's simply something at the moment we are using to practice. Next, evaluating these determinants. Let's start with the second one, 4 by 4 determinant. Let's see, we have 3 zeros. We have 3 zeros here. in the first column. Let's remember the sign diagram: plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. So if we expand it through the first column, we only use the first element because the rest are zeros. That's very good. So I can say we use the same element as it is. It's negative, therefore we keep the minus sign, because these signs in the diagram, they are not absolute signs. They are not, it must be absolutely positive, it must be absolutely negative. These signs simply tell us, do we need an extra minus in front or not? So minus 2 times the determinant of this, the minor of this. So that would be minus 4, 7, minus 3, 0, 1, 21, 0, 0, 3. And then it would be minus 0 times something, plus 0 times something, minus 0 times something, but we don't need to write all those zeros now. Now this 3 by 3 determinant can also be expanded in the same way through the first column. So we have minus 2 from the first term. Now doing this, I understand we have minus 4 times its minor, which would be 1, 21, 0, 3. Now this determinant, minus 2 times minus 4 times 1 times 3 times 1 times 3. We don't need to multiply 0 times 21. So as a matter of fact, 24, right? It's 24. As a matter of fact, what we see is we actually simply multiplied these elements on the main diagonal. We only have multiplied the elements on the main diagonal in this case. So we are very lucky with this determinant. We are very lucky because, basically because of all those zeros. We are lucky because we have zeros here, so we didn't have to write any other determinants there, any other factors, any other products, any other terms. Then we are lucky that we had zeros here, because then we don't have to write anything else after this. And of course, fortunately, we have a 0 there, which means I don't have to subtract 0 from 1 times 3. As a matter of fact, we have the determinant in the so-called triangle form. If the determinant is in the triangle form, that is, everything below the main diagonal is 0, then we can simply multiply all the elements on that main diagonal. We will look at it a little bit later. We still have 34 minutes or so. So we have time enough to consider all the interesting possibilities. Now, going to the determinant, fourth order determinant, as we see it. So we see that I have one row that has 2 zeros in it. That's a good idea to expand it through this row, right? But I have a still better idea. That would be, and that would be, in fact, what if I can make more zeros in that third row? In other words, I have one there, but I have minus 2 here. So what if I can make a 0 instead of that minus 2? To do that, I think, okay, minus 2, to make a 0 there, all I have to do is add 2 to this. All I have to do is add 2 to this. I will not do anything. I will just erase this, but the rest remains. Okay, something went slightly wrong, I'm sorry. I wanted. Just one moment. I have to pause the share and then resume, and then it works. I think. Yes, it does. Okay. Now it should be back to normal. At least in my, no, it's paused again. Resume slideshow. Yes, resume slideshow. There it goes. All right. So what I want to do now, I want to make a 0 here so that accepted techniques, the accepted rule is if I add another column to the fourth column, multiplied by some number to make a 0 there, then everything works out. In other words, I'm thinking that if I can take the first column and multiply, okay, I will erase all inks because otherwise it's a bit difficult. If I multiply this first column by 2 and add it to the fourth column. Why is that? That's because I want to make a 0 there. I want to make many zeros in one row. That's my trick, or that's my secret. To save myself work, I prefer to have a situation where I have as many zeros in one row as I can make. Well, 3 I can make. 4, if the determinant is not 0, I cannot make 4. But 3 I could. So I simply will multiply the first column by 2 and add it to the fourth column. So I will have, so rule number 1, in its own place here, the first column where it is, I'm not multiplying it there by anything. So I leave it as it is. Minus 1, 0, 1, minus 2. Second column stays as it is. 1, 3, 0, 4. Third column stays as it is. Minus 3. But the fourth column now will be changed. And it will be changed by taking the first column, multiplying by 2, and adding it to the fourth column. But I repeat, in its own position, the first column is still the same. I don't want to make numbers larger. I don't want to have bigger numbers. And I don't want to change the value of the determinant. And so minus 1 times 2, so the first element, minus 1 times 2 is minus 2. Added to this, we have minus 4. 0, the second element, times 2. Added to this is still 1. 1 times 2 is 2. Added to this becomes 0. This is the whole purpose. This is why we did it. This is why we are doing it, to make a 0 there. And finally, minus 2 times 2 added to the 0 is minus 4 again. And now I see that I can expand this determinant using third row. So third row, we know that it is plus, minus, plus, minus. We don't even have to draw the diagram all over. It's enough that we remember what the third row might look like. So it's this. So this is in the plus position. So we say, all right, it's 1 times the minor. Okay, to find the minor, cross out that row, that column, and we have 1, 0, minus 4, 3, minus 1, 1, 4, minus 3, minus 4. And now I have a third order determinant, this. Because the rest would be 0 times something, 0 times something, 0 times something. So I don't have to worry about those. I can write minus 0, plus 0, minus 0 to complete the row, but that's it. Now, it was 1. That's very good. 1 is always a nice thing to have outside. So in principle now, I only have to find this determinant, 1, 0, minus 4. So 1, 0, minus 4, 3, minus 1, 1, 4, minus 3, minus 4. I have this to find. And now I have had a taste of what it means to simplify a determinant. I want to do it again. For example, I want to make a 0 instead of minus 4. For that, I should take column 1, multiply by 4, and add to column 3, doing this. So the thing is, we can use any numbers, but 1 is the best number to eliminate something else. We are eliminating the number minus 4, this one. We are eliminating this number, and the best way in matrix rules to do it is take number 1, multiply by 4, and add to the minus 4. But if I do it with not one number, I have to do it with the whole column, all of it taken together. And so I will have 1, 3, 4 as it is, 0, minus 1, minus 3 as it is. And now 4 times 1 plus minus 4 is 0. 3 times 4 is 12. Added to 1 is 13. And 4 times 4 added to minus 4, 16 minus 4 is 12. So far, so good. So now I can again find the third order determinant using 1 times its minor, because the first row the rest of it will be 0. So it's 1 times minus 1, 13, minus 3, 12. So it's minus 12 plus 39, that's 27. So in principle, we see now why the properties of determinants, because using the properties of determinants, especially this property of multiply one column by some number and add it to another column, or multiply one row by some number and add it to another row, are very good to make zeros. So the more zeros we can make in one row, the easier it will be to find that determinant. Basically, what you should never do, I know that some people might be doing it, so what you should never do is expand the fourth order determinant by definition, especially if there are no zeros. So your first attempt should be make zeros, see if you can make some zeros. There are, of course, other possibilities. For example, I could take this minus 1, make 0 here and make 0 there, for instance, below minus 1. Going not with columns, but going with rows. And that's something that we will also do very, very often and a lot. Now, another matrix. So this is a matrix, not a determinant. See the round brackets. Round brackets mean that this is a matrix. So to find the determinant of M, or yes, we can write it like this. So it's 1, 2, minus 1, 0, 1, minus 2, minus 1, 1, 0, the determinant of this matrix. Now, of course, we can use whichever method we like. We can use the definition using the expansion. We may use, remember the diagonal method, where we copied 2 columns on the right-hand side, or now actually it would be a nice idea to add, see, we could add first row. If we add the first row down to the third row, we can make a 0 there. So actually I would say row 3 plus row 1, and I will have 1, 2, minus 1, 0, 1, minus 2. Again, if I add the first row down to the third row, in its own place, it remains unchanged. It's like you take a tool from the shelf, use that tool to fix something, like in this case, the third row, and then you put that tool back where it belongs, on the shelf. So you do not change it. You do not change that tool. For example, if you take a hammer and you want to draw some nails into a board or something, it's pretty much like this. We take this hammer, we draw some nails in the third row, and then we put the hammer back as it was. The hammer hasn't changed. And so 1 minus 1, adding row 3 down to row 1 down to row 3. So we could write row 3 plus row 1 is placed in row 3. 1 added to minus 1 is 0, which is why we did it. Now 2 plus 1 is 3, minus 1 plus 0 is minus 1, adding the first row down to the third row. And now we can expand it using the first column, as we see, and that would be 1 times its minor only. So 1 minus 2, 3, and I lost. Why did I lose a number? I shouldn't have. It's minus 1, of course. We added it down. Minus 1. And so what we have is, of course, the rest will be zeros because we have 0, 0 there. And so we have 1 times minus 1 is minus 1, and minus negative 6, that will be minus 1 plus 6 is 5. This determinant is 5. The determinant of the matrix M is 5. All right, I can write it like this. M determinant is 5. Now the determinant of minus 2 times M. Remember what happens when we multiply a matrix by a number. We multiply all rows, all elements by this number. So the whole matrix is multiplied by minus 2. Remember what happens there? The determinant then is multiplied by minus 2 times minus 2 times minus 2, because there are 3 rows that make us take the common factor outside. Times, of course, the determinant at 5, the determinant of this matrix. So minus 8 times 5 is minus 40. And the matrix itself, if I multiplied it by minus 2, of course, would look like, I will change the color to this, minus 2, minus 4, 2, 0, minus 2, 4, 2, minus 2, 0. So if you prefer, you could of course multiply the matrix by minus 2, as we do, and find its determinant separately here. Of course, it is possible. But in principle, remember that if you multiply the matrix by the number minus 2, it means every row is multiplied by minus 2. So from every row, as the common factor, which means minus 2 cubed. All right, so this was not about this, so this is something completely different. Now, the next case. In this case, if we compare, the second row remains the same, the third row remains the same, the first row is multiplied by 3. So this should be actually equal to 3 times determinant of the given matrix. 3 times 5, that's 15. Because only one row is multiplied by 3. So the whole determinant must be multiplied by 3. And the last one. So we, again, compare this to the matrix M. We see that here we have multiplied matrix by 4. This is actually determinant of 4M, because what we see inside here is 4 times the matrix M, which means we must take 4 cubed times determinant, which is 5. And so we have 64 times 5, that's 320 in this case. So this is, let's say, just an exercise in finding the matrix determinants. If we know some determinant, how to get something else. And now I do believe we have the determinant of a triangular matrix. We already saw that. If we have all elements below the main diagonal zeros, On the main diagonal, we might have a 0 or not. But if we have a square matrix and all elements below the main diagonal are zeros, we simply call it triangular. This is something that we already saw an example previously. And the determinant of this matrix is, of course, the product of all elements on the main diagonal, of all these elements on the main diagonal. So we saw this because we can expand by the first column, then times minor expanded by the first column, then times minor expanded by the first column, and so on. So in principle, if you can change a determinant in triangular form so that it becomes a triangle, this is a triangle, if it becomes a triangle, then in fact, you can find the determinant very easily. You just have to multiply all these numbers. The thing is that, of course, it's not always very convenient to do. Sometimes you will need to bring out common factors. But again, that would be something that is a little bit, well, or quite useful. So how we change the determinant into the triangle form. How we could change the determinant into triangle form. So one thing is that we should make, evidently, we should make zeros below the main diagonal. We should make zeros below the main diagonal. How to do it? And will the zero in the center of the determinant stay zero? That's another question. But we should like to have zeros instead of -4, 3, and 5. The problem is, of course, that as we do it, those other numbers will also change. At this moment, it's very clear. We can make 0 instead of -4 immediately, because we can take, okay, row 2, we could take row 2 plus 2 row 1. And of course, we leave it in row 2. We don't change row 2. We don't multiply row 2 by anything at all. Row 2 is never multiplied by anything. That is the first, because as soon as we multiply it and leave it in place, the determinant is also multiplied by the same number. So in principle, the basic row, the row stays there as it is. Remember, driving nails into a board. So 2, 4, 1, the first row is the hammer. The second row is the board. It stays where it is, and we only work with the hammer. If you like analogies. And so 2 times 2, okay, 2, 4, 1 at the moment stays as it is. Now we are improving, sort of. We want to improve the second row so that we have 0. Remember that our goal is to create 0, 0, 0, and then we will have some other numbers there, but we want to create zeros here below the main diagonal. So the order of work is exactly that. First column make zeros, second column make that 0, and then that's it. So we add the first row downwards times 2. 2 times 2 is 4. Added to -4 will be 0. 4 times 2 is 8. Added to 0 is 8. 1 times 2, 2. Added to -2 is 0. Now 3, 5, -1. Now we have a little bit of a problem. How to make 0 instead of 3? We could, of course, use fractions. We could multiply by a fraction, something multiplied by a fraction. However, I would do a trick. I will exchange the first and the third row. Of course, I will need to change the sign of the determinant at that, because I need to keep things equal. So 3, 5, -1, 0, 8, 0, and 2, 4, 1. I simply exchange these two rows. Why? Because now if I subtract third row from the first row, so if I think row 1 minus row 3, so now I'm going to improve that one. Why? Because I can make 1 there. I can make 1 there. I can make a unit. So we can actually do things in a different order as well. But in this case, why not? So this is one possibility. There are
Miss,
other
I'm sorry.
Sorry?
Can I ask a question?
Ask away.
The second row, what did we do? How did it become 0, 8, and 0?
We took the first row, we multiplied it by 2 and added it down to the second row. That's what we do. This is the method that we will use in matrices a lot. This is only the first acquaintance with this method, but we will have it at least one more time, but actually we'll have it more. So I take these numbers, the first row, multiply them by 2, and add them to the second row. The aim was to get 0 there. Accidentally, we also got 0 here, but that's neither here nor there. It doesn't necessarily happen. So in order to create zeros, in order to create numbers we want, like 1, for example, is also a good number, we can take one row, multiply it by some number, and add it to another row. Like take a hammer and drive some nails into that board. So the row multiplied by something displays the role of hammer, driving nails in the second row to make, let's say, the 0, for instance. And now, actually, it would be rather difficult to get rid of 2 as it is. So I will actually take row 1 minus row 3. Why? Because that will give me 1. Because 3 and 2, the difference is 1. I want to make 1 there. So 3 minus 2 is 1. 5 minus 4 is also 1. And minus 1 is minus 2. So I did this. I took row 1 minus row 3. Now 0, 8, 0 we do not touch. And row 3 itself is playing the role of the hammer, so it also stays unchanged and is placed back where it belongs. So we simply borrow this in order to improve another row, and then we put it back as it was. Why is this good? Why is this better than previous? Because now I can take 1 and make 0 there. So in fact, I will take row 3 and minus 2 row 1. I will multiply first row by minus 2 because I want the number opposite to 2. I want to make 0 there. And so we have still a minus. We still have 1, 1 minus 2. We still have 0, 8, 0. And now, multiply by minus 2. 1 times minus 2 is minus 2. Added to 2 is 0. This is what we wanted. This is what we wanted. Now, of course, we have to do the same with the other elements of the first row too. You cannot do something only with one element. You have to take the whole row. And so minus 2 times 1 is minus 2. Added to 4 is 2. Minus 2 times minus 2 is 4. Added to 1 is 5. And now we would like to have 0 below 8. And again, I will do a little trick. So I have this minus sign dragging through the whole thing. Now I would actually like to exchange these two. So this is a little bit like playing chess. You have to think some moves ahead. So in this case, I'm generally thinking one move ahead. One move ahead is enough. If I exchange these two rows, I have two benefits. First benefit, this minus disappears because I changed the sign again. 1, 1, minus 2, 0, 2, 5, 0, 8, 0. And the second benefit is now I can make a 0 there. If I multiply the second row by -4, I get -8 instead of 2. And adding to the third row, I get 0. So I will have row 3 -4 row 2. So this takes some getting used to this whole thing. Of course, this is something completely new, playing with numbers like that. But it turns out to be very, very important for matrix algebra. So row 2, 0 times -4, of course, is 0. So first row unchanged, second row actually now unchanged. Now 0 times -4, 0 plus 0 is 0. 2 times -4 is -8. Adding down to 8 is 0. This is why we did it, to make the 0 here at this point, to get rid of 8. And 5, this was not a -5, this was a 5, looks like a minus. 5 times -4 is -20, added to 0 is -20. So now we have a diagonal matrix because I have those zeros below the main diagonal. So this means the determinant is 1 times 2 times -20. So it is -40. This is actually the same matrix we already had last time. We already had a matrix like this with determinant -40. I think it was exactly the same matrix. But the manipulations that we can do, we can find determinant of a matrix by creating the triangular form. I'm not saying this is the easiest method, it's not. But this method is useful because we need to get acquainted with it. We will have to use this method further in the course next week or the week after that perhaps. We will need this method. So the idea, I want you to get used to the idea. We can take a row, multiply by some number, and add it to another row to change that other row. We are not changing the row we took and multiplied, but we are changing another row. We are using one row to improve another row. What's improvement? Getting zeros in nice places is the main improvement. Getting zeros in the places we want, because that makes us, let's say, that helps us to find the matrix, to find the determinant values more easily. Now let me check. We have 4 minutes approximately. Again, changing into the triangle form, this might be, well, we can do probably the other determinants. We will start with practice next time on Monday, because practice is important, and determinant properties and determinant practice is important. We will do some practice on Monday as well. So let's try to change this into the triangle form, and that will be the last thing we do today. So actually, it looks like I could make 1 and I could make zeros below it. So the plan is to make zeros here. I don't care what happens in the top left corner. I'm interested in having zeros below. Then the next step will be making zeros here, going downwards. And the third step will be making a zero step. And then we will have a triangular form. The process is such that the numbers on the diagonal will change. They will not be 2, 1, 1, 1. They change along with the other numbers. We cannot avoid it. And that's why we cannot say that the determinant is already 2 times 1 times 1 times 1. It's not. It's not. Because as we change the circled numbers now, the other numbers in the matrix will also change along with them. You cannot simply change one number as it is. And so, remembering that 1 is a very good number, 1 is a very good number because it helps us change other numbers. So I might do something like this. I will use, it's just a little bit like chess. You can choose the order of operations, you can choose what to do, and what you choose basically depends on many things, perhaps, on what you might like. And now let's have a look. Let us take the last row and add up to the first row and add up to the second row. Why? Because then we will get 1 instead of 3 and 0 instead of 2. And then we will simply exchange some rows. So, we can start by exchanging rows, no problem. We can start by perhaps exchanging first row and second row. Why not? Why not? So we can have 3, 1, minus 2, minus 2, minus 1, 2, minus 1, 0, 1. Because of that, we need to change the sign because we swapped 2 rows. And then we have 0, 2, 1, 1, and we have minus 2, 0, 2, 1. And in this situation, I could say, all right, I can take row 1 plus row 4. That will make a 1 there. And I can take row 2 plus row 4. That will make a 0 there. Or afterwards, I can take row 2 and add it downwards. It doesn't really matter much. In the end, I will still have something to eliminate. So let's do it this way. Row 1 plus row 4 makes 1, which is the reason we are doing it. Now 0 adding up to 1 is 1, 2 adding up to minus 2 is 0, and 1 adding up to minus 1 is 0. So this is what we got. This is what we got. Let's erase this and make it nicer. This is what we got when we added row 4 up to row 1, and the minus is still there. If we have a minus there, then we have a minus there. And now row 2 plus row 4. So take row 4, add up. So we make minus 2 plus 2 is 0. 0 plus minus 1 is minus 1. 2 plus 0 is 2. 1 plus 1 is 2. Third row for now stays as it is because we have this 0. And then we have minus 2, 0, 2, 1. Because we have only improved these first 2 rows. But we already have a 0 in the third row. Now we need a 0 here. But we can do it easily. That is row 4 plus 2, row 1. Because 1 times 2 plus negative 2 will give us that 0. So we have minus still in front. Nothing has changed yet. 1, 1, 0, 0. 0 minus 1, 2, 2. 0, 2, 1, 1. And the fourth row, double first row, 2 and minus 2 is 0, which is why we are doing this particular thing. The aim, we don't do it at random. We always make a plan. And the plan is we go basically down 1 column, then down next column, then down next column. So row 1 times 2, 2 plus 0 down is 2. 0 times 2 is 0, plus 2 is 2. 0 times 2 is 0, plus 1 is 1. All right. Now we should make zeros below 1, so we should make this next step. And the next step is making zeros here. So it's all very, very planned. We follow a plan. We don't do it at random. If we follow the plan, this is a good idea because now we will use the second row going down. We won't touch the first row. because if I do it with the first row, I will destroy my zeros in the first column. I don't want to destroy those zeros. So I'm not touching the first row anymore. I will only touch the second row. And so I will have row 3 plus 2, row 2, because minus 2 plus 2 will create a 0, and row 4 also plus 2, row 2, again to create that 0. So we have minus, it's still in front. First row is still not touched. Second row is just the tool, and therefore it doesn't change. Now, times 2, add down, 0, times 2, add down. Now this also becomes a 0. 2 times 2, 4, add down becomes 5. 2 times 2, 4, add down becomes another 5. And in the third row, somehow I keep jumping between these things. I don't know why. And finally, second row times 2 added down to the fourth row. 0 times 2 plus 0 is 0. Minus 1 times 2 is minus 2 plus 2 is 0. 2 times 2 is 4 plus 2 is 6. 2 times 2 is 4 plus 1 is 5. All right. Now, if I could only make 0 there, I would have this diagonal form. But to make a 0 there, well, what could we do? We could, for example, take 5, the common factor, out. Or we could multiply the third row by negative 1.2, because 5 times 1.2 would be 6. So we don't have to take the common factor of 5 out. We can, we don't have to. So I can still use minus, I can still use 1, 1, 0, 0, 0, minus 1, 2, 2, and then 0, 0, 5, 5, and here I will have row 4 minus 1.5 row 3, 1.2 row 3, because 1.2 multiplied by 5 will give me 6. And I need 6 to destroy this 6. So, of course, zeros don't change anything. Now, 5 times minus 1.5 is minus 6, so that makes a 0 there. 5 times minus 1.5 is minus 6, plus 5 makes minus 1 there. That's it. So now we have the triangle form. Now we have the numbers on the diagonal. We multiply them. We have minus 1 times 5 times minus 1 is 5, and another extra minus in front. So the determinant is minus 5. This particular determinant is minus 5. As I said, this is not the convenient method. This is not the convenient method. The most convenient thing actually is make 3 zeros in one row by whatever means. For example, if you make 3 zeros here at this moment, it is already something very, very good for us. We can work with this, expand through the first column, for instance. Or I could see if I only had 2 zeros in one row, for example, from this, I could also simply go there and create a 0 here, and then expand through the first row. So there are options. You don't have to make the triangle form. It's sometimes useful, but it's more useful as practice for the future. For practical purposes, to find a fourth order determinant, it is enough to create 3 zeros in one row or 3 zeros in one column. And it doesn't matter what this other number is, because you will multiply it by the minor. All right, so on Friday, we will have a lot of practice. These things, evaluate the determinant, this determinant, this very nice determinant, and so on and so on. So I am already 7 minutes over time. I apologize. because normally we have 1 hour 35 minutes for a lecture. That's meant if we take a 5-minute break, for example, in the middle of the lecture, if we are very tired. Normally it's 90 minutes. Normally it would be 90 minutes. So apologies, and well, if I can, another time I will try to finish early. But on Monday, we will start by evaluating these determinants. However, if you can manage a little bit of practice until Monday, by Monday, you're absolutely welcome to do this. The answers are in the answer file. And today's file is, okay, where is it? Number 1-3. It's 1-3, the third lecture, all determinants and their properties. Basically, in these last 2 lectures on Wednesday and today, we learned how to compute determinants. There is a definition, and you can always use a definition, it works, but actually it's very good to know some shortcuts. If you can use some shortcuts, you will be able to find the determinants more efficiently, faster, less chance to make a mistake, and so on and so on. So basically, for 4x4 determinant, the best option would be make 3 zeros in 1 row or 3 zeros in 1 column, wherever you can. Even 2 zeros would be good. Even 2 zeros would be good. It would still make things easier for us. All right. So I will see you on Monday at 10:15 in the morning, and we will continue from somewhere here. I hope everybody has remembered to write their name in the Zoom chat.